So today we're going to look at how to calculate the linear correlation coefficient using PSPP. So here in our fictitious data set, we have two variables. One is screen time, and these values are in hours, and this is sleep time. So say there's an assumed relationship or an assumed correlation, some form of association. And just remember that correlation does not necessarily mean causation. It just means that as something is happening to one variable, something is also happening with the next variable, and there's some kind of association between the two, but not necessarily meaning that one causes the other, right? Because it could have confounding variables or other variables causing a certain effect. But yes, so I want to look to say, what is this relationship like? Or suppose someone comes and they make a claim that there is a linear relationship, meaning that as one increase, the other decrease. Or as one increase, the other increase. Or as one decrease, the other decrease. So we want to find a way now, how do we test if this relationship that we're seeing is truly linear? So in order to that, you have to do the linear coefficient test, the linear correlation coefficient test. And we could do that using PSPP. But however, first let's look at some requirements or assumptions for this test. So to test the linear correlation coefficient between two variables, especially when we're making inferences about a population for using a sample, we have to ensure that the data was collected using one of the random sampling methods, and that it's paired quantitative data, not just any data. But once you're looking at linear correlation coefficient, you need paired quantitative data. And the second requirement is that the pairs of X and Y data must have a bivariate normal distribution. What we mean by bivariate normal distribution? It's not just, it does not simply mean that each variable must be normally distributed. And yes, that will be good. But what it means is that when you look at the data set, there might be a certain value of X that has multiple values of Y. So all those values of Y for each of those X values must have a normal distribution, and the other way around. So different values of Y would have various values of X that correspond with it. Then the distribution of those values of X for each one of those values of Y must have somewhat of a normal distribution. So this might be a little bit confusing to understand. So for simplicity's sake, just ensure that if you do a scatter plot of X and Y values, you will see an approximate straight line pattern. And that will tell you that more than likely there is a bivariate normal distribution. Also ensure that if outliers are known to be errors, you remove them, because that would significantly affect the value of the correlation coefficient. And if there are outliers that weren't errors, if you plan to remove them, ensure that you see what is their effect. So what is the correlation coefficient before and after you remove them, so you could know if these outliers were significantly affecting your data set. So yes, let's perform this linear correlation coefficient to see if there's actually a linear relationship between sleep time and screen time. So as I said, to test this, the first thing we want to do is to look at a scatter plot to see if we're actually seeing a straight line. So let's go to graphs, scatter plot, and we could put screen time on our x-axis as the independent variable to see how it's affecting sleep time, right, which would be the dependent variable. I'll put that on the y-axis. And let's click OK. And here we have our scatter plot. And if you look at this scatter plot, you could see the pattern of somewhat of a line coming down. So bear in mind, this is a fictitious data set, and it was designed to help for teaching purposes. But you could see a line. You could visualize the line of the data points coming down here, which is showing that as screen time increases, the time for sleep is decreasing. So seeing this nicely shaped scatter plot, we could assume that there's somewhat of a line there, and we could make the assumption that there is some bivariate normal distribution. So now we could proceed with going to do the actual test to get an idea of what the linear correlation coefficient is. So here we'll be going to analyze, and you're scrolling down and you will say bivariate correlation, and you click bivariate correlation. So here it doesn't really matter, it wouldn't ask you for who is on the x-axis and who's on the y-axis, because depending on whichever variable you put on whichever axis, the value of the correlation coefficient remains the same. And if you change the units from hours to minutes, or from minutes to hours, or one of them is minutes, one of them is hours, the value will remain the same. And we're going to leave it here as a test, the test of significance, as two-tailed. And we're going to send over each of them. And we'll click OK. And here we get our output. And our output here is showing here, when you see here 1, 1 means a perfect correlation, and that is because this is between screen time and screen time. But we want to say between screen time and sleep. So here we have a negative correlation of 0.771. So to have a correlation of 0.771, it indicates that this is a strong correlation. And as we see that it's negative, and the negative will indicate to us that it indeed, as we see, where screen time was increasing, sleep time was decreasing. And if you want me to just pull up our scatter plot again, you see here on the scatter plot, so it's showing here. And this is why, because as screen time is increased, sleep time is decreasing. So that is why you have a negative correlation here. And because it's 0.7, which is closer to 1, it indicates that this correlation is strong. And if we look here at the p-value is less than 0.05, which tells that this is significant. If it was greater than the alpha of 0.05, that would mean that yes, there is a correlation, but at the population level, it might not really be a linear correlation. But because the p-value is less than the alpha of 0.05, then we'll assume now that the correlation is indeed a linear correlation. And that is how you perform this test using PSPP.